Good morning, everyone, and welcome to today's webinar, Open Networking Becomes a Reality. Are you ready?
My name is Judy Ash, and I'm the head of corporate marketing at Big Switch, and I'll be your host for today's webinar.
Really excited to welcome Ellie Karpolowski, Director of Product Marketing from Broadcom, and Rob Sherwood, our own Chief Technology Officer here at Big Switch Networks. As we go through the presentation today, please feel free to ask questions. As always, use the Q&A box on your webinar dashboard. If you're watching the video from a rebroadcast or on demand, and you have questions on a particular upcoming webinar topic that you'd like to present or like to hear about, just go to bigswitch.com/webinars and submit a question using the link provided. We have also provided you with handouts for today's session, and you can download those from the Handouts tab on your dashboard. It's super easy. Our first speaker today is Rob Sherwood, Chief Technology Officer here at Big Switch.
Thanks, Judy. How's everybody doing today? This is a lot of fun for me. I'm here with my partner in crime here, Ellie Kasparowski from Broadcom.
Very nice to see you again, Rob. Good morning.
And today we're going to be talking about one of my favorite topics, which is open networking. This is a webinar series that we're trying to lead off with some of the support that we're actually now going to be shipping OpenNSL with Open Network Linux, and the hope is that's going to make it easier for people to do lots of different networking programming bits. And so for this webinar, we're going to do a quick recap of what is Open Network Linux for people who don't know what that is. We're going to talk about what is OpenNSL for people who don't know what that is. And we're actually going to jump way down into the weeds, and we're going to talk actually about what does programming in ONL and OpenNSL start to look like. And then we'll open it up for some discussion, see if anybody has any questions. Apologies for folks who have heard this before, but just to get everybody on the same page. Open Network Linux is a Linux distribution for bare metal data center switches. It is a reference network operating system. It's part of the Open Compute project. And you can think of it as the standard collection of software packages, utilities, drivers, abstractions, all sorts of stuff that you need to make a network operating system. In other words, it's a NOS that ONI would install. And we've actually had a lot of success with Open Network Linux. We've had all sorts of partners get involved. We've had Acton, of course, we've had Broadcom, we've had Facebook, NTT, others. There's a lot of interesting stuff going on in this space. People ask me, okay, well, what is Open Network Linux good for? So one thing we like to think it's used for is just basic hardware testing. So if you have a Open Compute project switch and would like to verify that this actually works, we've got all sorts of drivers. We've got an open source reference implementation for people to use. Another is for do-it-yourself packet forwarding. If you really think that you would like to write your own networking protocols, if you think you can do better than BGP, if you want to just try something out on your own, this is a great place to get started. The barrier to entry for people to understand all of the bits that go into making a functional NOS is actually fairly high, but we like to think we've lowered the bar for that, and it's now easier for really just kind of hobbyists and academics to start playing with this. But last and maybe most importantly, Open Network Linux is a great building block for commercial products or actual real production-grade software solutions. And in fact, this is what Big Switch's commercial products are based off of. If you're familiar with our Big Monitoring Fabric product or our Big Cloud Fabric product, both of these build on the operating system we install on the switch, which is our Switch Lite operating system, and that's based on Open Network Linux. And so if you want to build a commercial-grade network operating system, Open Network Linux is a great place to get started. I've talked in other webinars about where ONL has had traction, but just briefly, Open Network Linux is part of the ON Labs Atrium and Cord projects, and that's been fairly successful. If you're interested in Facebook's FBOSS, Open Network Linux is really one of the easiest and best ways to get your hands on that. And we've also done some work with NTT as part of the basis of their GoBGP project. And so if folks are interested in learning more about those things, please check out the Open Network Linux website, and we can point you to more details on that, but that's not really the subject of what we're talking about today. Open Network Linux supports lots and lots of different types of hardware. We have compatibility right now for 25 different types of data center switches. We have all sorts of different CPU complexes in terms of x86, PowerPC. We've recently added support for various ARM architectures. We've got 1 gig, 10 gig, 40 gig switches, now even 100 gig switches. And we've really got a real critical mass of switches that we're starting to support. It's really become the case that almost every switch that's going into open networking is getting an Open Network Linux port. And so that's kind of exciting. Just at a software level, a software block diagram level, if you imagine you've got some sort of switching hardware, whether that is a Facebook wedge or an Acton 6712 or something like that, and then that box will have a packet forwarding chip, probably from a company like Broadcom. It will have some sort of CPU, ARM, PowerPC, and it'll have all sorts of miscellaneous sensors. And then Open Network Linux supplies the Linux kernel with all the associated kernel drivers, critically with a platform abstraction layer on top of it, along with the relevant SDKs that come from various companies. Specifically, basically our best support right now is with Broadcom, and we'll be talking today about OpenNSL, the open APIs to this stack. And then you can take that stack and combine it with your choice of packet forwarding application on top. That is either something from, for example, Microsoft with their Sonic product, or Facebook's FBOSS, potentially even the Indigo OpenFlow switch that we've worked on together, or even newer things like companies like SnapRoute, if you're familiar with those. So there's a fairly interesting software ecosystem going on here where, much like in the traditional Linux world, it's really up to folks to kind of compare and contrast and decide which of the various components that they want, which of the things they want to write themselves, and it's a fairly vibrant ecosystem. Even more important is that you can actually write your own applications in this space, and so that's fun as well. So that is a quick overview of what is Open Network Linux. Let me hand it over to my partner in crime here to talk about specifically OpenNSL.
Thank you, Rob. Good morning and good evening, everyone. My name is Eli Karpolovsky, and today I'll talk about the Open Revolution that my friend here, Rob, started kind of building the blocks here. So when we're talking about networking, it's evolving from closed system where hardware, firmware, and application software are supplied by a single vendor to an open system where a customer can choose software independently of the hardware. All right? So this transition from closed to open system is commonly referred to as what we call, the network disaggregation. In addition to separating the software from the hardware, the end user want to build their own environment and their own specific application on top of the bare metal hardware supplied by the ODMs. So in order to accelerate the development of open application, Broadcom, as the leading silicon vendor, provides a set of open APIs that enable access to the hardware resources. Now, when we look at opening up or building open clouds, we really see 4 key requirements from our partners. The first one is build open network OS. And I think, Rob, you kind of start mentioning this, and we'll talk a little bit about this later on. The second thing is end customers that build open source application and maybe want to share them. The third reason for using such an environment is optimizing the switch hardware platform development. So you want to quickly accelerate the time to market of new. And lastly, we see this as a growing trend where OEMs expose APIs directly to their end customers. So Broadcom has developed the Open Network Switch Library. This is what OpenNSL stands for, which is basically a suite of open network switch APIs that exactly address that by providing open and direct access to the Broadcom Strata XGS and soon the Strata DNX switches. The OpenNSL software allows customers to build application on the industry most widely deployed merchant silicon without the need for a software license agreement with Broadcom. Our OpenNSL APIs are also published on our GitHub, on Broadcom GitHub. So let's dive into the details. So let's start with building open network OSs. Since we announced OpenNSL, Broadcom has worked very closely with the leading ecosystem partners to develop some of what we believe to be the key innovations for data center networking. If we look at the OpenNSL today, we support many of the open OSs available, and we are working on a few others that will be announced soon. So from OpenOS, OpenSwitch, to FOS, entity layer 3 routing, to supporting SCI and Sonic. And of course, Rob, the Open Networking Linux, Broadcom provides the best solution for each open project today. And of course, we will continue to foster innovation on our switch silicon. Moving on to the open source application. This is actually very, very interesting for us because by using the OpenNSL, end customers can now build their application directly on top of Broadcom switch ASICs. This enables a growing number of end customers that deploy Broadcom-based platforms, either on XGS and later on DNX devices, to maintain their investment of their unique applications. So one example of such application is the Broadcom Broadview agent and application, what we call the analytic application. So that is probably the #1 application that we see in the industry today. The next bullet is optimizing switch hardware platform, and I think this is a key one. To support the community, OpenNSL released a binary for specific platforms on GitHub, right? So customers can use these binaries to build application without signing the SLA with Broadcom. But if they want to build new or different platform, we also provide them with that, right? So they could work directly on what we call the CDP, the Community Development Package, which enable them to use a similar platform with the existing OpenNSL binaries, but with a new platform initialization file. This method could be used when you want to build new platform to be supported in a similar, I will say, device to the existing platform. The existing binaries and libraries can be reused, and in order to support the community, those config files are actually published into the public domain. So one can take that and reuse it later on. The other option is to use what we call the ODP, the OEM development package, and that is of course with an SLA with Broadcom. You could use the ODP to create a whole new platform. We believe that over time, taking these two methods into market, we will have a robust, a broad range of platforms to be supported by the community. Okay, so the last one is the OEMs that now expose APIs to their end customers. And this is a growing trend. We see more vendor partners that offer OpenNSL to their end customers in order to support in-house designs of application. And by that, we think that what they really offer is increase the value of the user investment and reduce his CapEx. So this is key, and we see this as a growing trend. Now, when we started this OpenNSL project, and this was, Rob, correct me if I'm wrong, I think it's about a year and a half at the OCP Summit of 2015, we opened up about 90 APIs. And this is really to support the first OpenOS named FOS by Facebook. Today, we have over 500 APIs that is available, and we have new release of OpenNSL every quarter to basically enable more and more APIs and more functionality. It is fair to say that OpenNSL today offers more than enough APIs to support a modern open network OS for the data center applications. And just to summarize everything that we discussed today, here's really the benefits of what we believe OpenNSL provides to our application developers. First, it provides access to the familiar programming model of the Broadcom SDK. There's a close relationship with the corresponding Broadcom SDK APIs that is proven to work on multiple silicon platforms. So really using the OpenNSL enables the community that is already familiar with the API to build a bare metal platform that offer a robust feature set, and of course that will reduce the time to market of a new platform or a network OS, or of course an application. As mentioned a few times before, allowing application developers to open up their application down to the API level with an immediate access to the richest feature set and the highest performing networking silicon in the industry, I think this is probably the main motivation for many of our customers. The ability to basically say, I want to add 5, 10, 15 new APIs to address these specific features, and that will take most likely, from our experience, less than a month to get it up and and public into the GitHub. This is a key capability that provides us a very flexible and robust way to address our customer needs. And of course, building up your platform simplified is another key value to the growing ecosystem of SDN and cloud customers using OpenNSL today.
We got a question here, Ellie, that might be worth answering now. They're saying, when will OpenNSL support the DNX line of chips?
Oh, that's really a good question, because it's a good question because we have a direct answer very soon, meaning October timeframe. So by October, we believe we're going to have, or let's say Q4, we're going to have pretty much most of the features that were already supported on the XGS will be ported and supported by the DNX family. And we're going to start with the Qumran device.
Awesome. There's definitely some really interesting hardware capabilities in the Qumran stuff, so I'm excited to look forward to that. That's kind of an overview of what is Open Network Linux and what is OpenNSL. Let's actually jump down to the API level and talk about, okay, well, how do you use these things? So if you're not a programmer, the rest of this might be a little bit low level for you. But if you're not, don't worry. It's not that to use these things you have to be a programmer. There's actually quite a bit of interesting example code that you can actually just grab and use. So actually shipping directly with OpenNSL, more for API examples, there's actually an example routing package that you can look at, and there's the link here. If you're looking for something that has a thrift interface, so Facebook's FBoss has open source code that you can look at that makes direct OpenNSL calls, as well as SnapRoute's FlexRoute, if you're familiar with that. And so here's a URL there. And I honestly think that these are just the tip of the iceberg, that really the ecosystem that's getting unlocked here and the APIs is really just going to create a groundswell of new open source projects using these APIs. So I think this is just the beginning. So for the rest of this, I'm going to be talking about specific code examples, and feel free to fall back to any of these if you have more questions. We won't have a chance to go super into the lowest level of debugging detail, but the idea is just to highlight the things that you as a programmer might want to care about if you're doing OpenNSL programming. And so before I get to that, I want to talk about the things that you don't have to care about. So there's a whole lot of work that goes into programming an embedded switch that, fortunately, with Open Network Linux, you don't have to care about. So if you've ever done embedded systems programming, one of the things that's one of the bigger pains is actually the build environment, just making sure that all the cross-compilers work and that all the tooling is correct. ONL solves all of that for you with a Docker image. We provide a single Docker image that pre-installs all of the cross-compilers and tooling and libraries and everything that builds stuff for Open Network Linux. And it works across x86, PowerPC, ARM32, and we're just about to have ARM64 support land. Another thing that you typically have to worry about, but don't with Open Network Linux, is the environmental bits. Trying to get the fans and the power supplies and any of the field replaceable units, the FRUs or the LEDs and all the stuff to run so you don't bake your box, or just so you aren't deafened by the aircraft carrier sound of a fan at 100%. All of that's handled for you as well. We have a separate process, the ONLPD, the Open Network Linux Platform daemon, that does all that management stuff for you. So you don't have to worry about any of those things. Also in terms of the box management, it sounds like it's a stupid problem, but it's actually a horrible pain, is trying to get the same version of the kernel to work with the same version of OpenNSL, which implicitly has kernel modules from Broadcom's underlying SDK in it, with the compiler, with the libc, to have this version issue managed for you out of the box really kind of lowers the barrier to entry to doing switch-level programming. And the last is actually the optics, and particularly in multi-chip PHY programming, there's a whole bunch of stuff that actually, honestly, you just don't want to have to worry about. Like when you plug in an SFP, there's an online negotiation process that involves reprogramming parameter settings and things like that, but it really doesn't add value to your program. It just makes sure that the bits can flow. And we have software that helps you solve that as well. So jumping into it, before people even start to look at the Broadcom APIs, there's a bunch of things that are worth starting to understand. One is pervasive across the APIs. There's this notion of what's called a unit. And if you just look at the documentation that exists, and if you just look at the header files, it's not clear, at least it wasn't clear to me, what a unit is. And a unit is really just an identifier for a chip. Some boxes actually have multiple Broadcom chips on them, And most of the commands say you have to actually program these chips individually. So you have to say, I want to program chip number 1. I want to program chip number 2. So for all the examples that I have, and actually most of the switches that Open Network Linux supports, there's only a single chip. So unit will just be the integer 1. The other thing to be aware of is there are a couple different instances of the OpenNSL library. So you could actually just go to GitHub, as Ellie mentioned, and download the binary. But that binary is coupled to a specific kernel on a specific platform. You're probably best not using the binary off of GitHub. You should use the one that comes with Open Network Linux, particularly because it internally will use things like our ONL switch APIs, which does the PHY and the port mappings and things like that. Short story, use the one we provide. Otherwise, you can run into all sorts of problems that you may not be aware of, and frankly, you don't have the code to debug. The other thing to be aware of is when you're programming an ASIC, even more generally than for Broadcom, more of these chips have what I would call a packet forwarding pipeline, and I'll talk about this in the next slide. But you don't have this typical run to completion model that you would have in an x86 world or in even like a network processor world. You have a very fixed pipeline of this action has to happen before this action has to happen before this other action. And that's because these chips actually perform orders of magnitude faster than standard general purpose processors. That's why they're application specific. But it does require a little bit of mind mapping to understand how to make these chips work. And the last is actually working with the OpenNSL library provides a whole bunch of value, because what's happening under the covers is that the raw registers of the underlying chip are memory mapped into user space, and this is trying to provide an abstracted view of the scary register level details. And so sometimes you have to be aware of this, but most often than not, OpenNSL does a good job and solves this for you. So just a high-level view of what it takes to program OpenNSL. This is actually an abstraction of the Broadcom pipeline. This is actually out of the OFDPA documentation, but I quite like this picture. You can think of each of these little blocks like a little mini processing pipeline, a little mini decision. Like, so if a packet comes in and matches a certain ingress port, what do we do with it? When does a packet go from, when do we route packets versus multicast packets versus bridge packets? And then independent of that, it always goes to a table where we can check the ACL policy. There's quite a bit of documentation on the OpenNSL website about this, but it's useful in my mind to have this view as you're trying to program the chips to understand where decisions happen and which pipeline stages do what. So in the time we have remaining, I am going to try to, and this is perhaps somewhat ambitious, but get through what I think of as the list of the relevant API calls to set up basic L2, L3 packet forwarding. And, at some level, it's just 5 easy steps, but obviously there's a lot of devil in the details here. So this is the summary slide. We'll go through each of these individually. But so step 1 would be to set up your slow path, and I'll describe what that means. But the slow path is generally used for your control plane protocols. That is your ICMP, your spanning tree protocol, your LACP, routing advertisements. That's what anything that's not handled by the Broadcom chip itself, that's your slow path. The next thing you have to do is define your port to VLAN mappings. Past that, you set up your L3 interfaces. An interface is something that you can imagine you can ping. And then you manage your next hop entries. That is, where are the things you're going to afterwards. And then last, you actually install the routes. And I'll walk through each of these in total. But if you can pull off these 5 steps, you actually get some actually functional basic L2, L3 packet forwarding, which is kind of cool if you think about it. So step 1, setting up the slow path. So I will define the fast path as any operation that stays local to the ASIC. And the fast in this context really means line rate. And so depending on the ASIC, you can get anywhere between 1 and 3 terabits of throughput. And this is actually really quite fast. On the other hand, if there's things that the ASIC itself can't handle, and that's any sort of control plane protocol, any packet with IP options, there's a whole bunch of packets that the ASICs are really not set up to handle. You have to punt the packet across the PCI bus to the CPU of the switch, where you actually are now processing that packet in a standard user space process. And that slow path is orders of magnitude slower. Depending on how you tune things, you can get it to go faster than 100 megabits per second here, but that's a good rough rule of thumb. And so the idea is you only want very small numbers of your packets to traverse the slow path. It's really your job as a programmer to ensure that most packets stay in the fast path of the network. But we also need to set up the transition between the slow and fast path. And so at an OpenNSL level, there's really two relevant APIs. And these are covered across 3 different header files. There's the packet.h, the transmit.h, and the receive.h. And so the transmit.h is actually fairly straightforward. You build up a packet, and built into that packet structure is both the data of the packet as well as the port you want it to egress and some other metadata. And then you say, I want you to send that packet out a port off of chip number 1. And so that's reasonably straightforward. The receive function is a little bit more complicated because this has to be fairly optimized. This can be a heavily run code path. So what you do is when you actually register a callback. So the idea is you say, okay, off of chip number 1, I'm going to give my callback some sort of meaningful identifier to me. Maybe this is the ICMP callback. I'm going to specify a callback function. Every time a packet comes in, call this callback function. And I'm going to give that callback a couple different bits of metadata in terms of the priority, a cookie to pass into that callback just so I have some context. And there's actually quite a long list of flags that you can provide for different types of quality of service and things like that. And then once these 2 things are set up, we'll talk about later, particularly in step 5, how to actually program the fast path to send packets to CPU so that things like ICMP, like if somebody's trying to ping your router interface, you can actually handle that. And it's a little bit of an aside, but I think it's kind of cool. If you imagine punting all of your packets to CPU, you could actually, with all of the ports of a Broadcom chip, you could actually create an ultimately extremely slow but very functional complete router purely in slow path. So after you set up the slow path, step 2 is to set up your VLAN mappings. So something that's surprising to almost everybody who's done programming on these chips is, and it's kind of obvious if you think about it, but it's just not obvious at first, is that all packets inside the ASIC are actually VLAN tagged. And that's totally independent of how the packets arrive. So if you have an untagged packet, the first thing that you have to do is tell the chip, yeah, I know it came in untagged, but internally this is part of VLAN number 10, or internally this is part of VLAN number 20. Or maybe it came in tagged for VLAN number 10, but I want to do a translation to number 20. And so there's 3 relevant calls that you have to do to set up the VLAN mappings correctly. And of course, there's a long litany. This is kind of just the quick overview. But step 1 is you actually tell the chip that you want VLAN number 10 to be active, and that's simple. You use the OpenNSL VLAN create call. You tell it which chip, and you give it a VLAN number. And so you have to call VLAN create for any VLAN that you're going to use before you use it. The second is that there is a data structure called a port bitmap, which contains a bitmap of which ports. And there are macros for clearing that. There are macros for adding to that port. And then you actually set per VLAN which ports tagged and which ports untagged have access to that VLAN. So if you wanted to put all ports untagged in the same VLAN, you can do that with a single call. And the last, step C, is there's a single call OpenNSL port learn set that you can enable MAC learning on a given port. And so once you do all of these, you actually have enabled standard switch functionality. So if you are only interested in building an L2 switch, just doing these first 2 steps actually does that for you, at least in a very basic kind of hello world kind of way. Now let's start looking at some of the routing bits. So step 3 is actually to set up an L3 interface. So the code actually calls this an ingress interface. You can think of this like the thing that you would try to ping. So if you imagine an iOS, if you set up interface VLAN 10 and gave it an IP, that's the thing we're configuring here. In our Big Cloud Fabric product, if you set up an interface for a segment and gave that an IP, that's the thing we're configuring here. It's really the logic on the chip that marks this specific MAC address in this VLAN. If you send to it, I want you to treat that as a router interface, and I want traffic sent to that IP, sent to that MAC address. I want that to be routable. And so all of these are helpfully in the OpenNSL L3.h header file. There is a data structure called L3 interface, There's an initialization function that just kind of zeroes out a bunch of stuff. And then you push into that structure, and there are fields that are reasonably self-documenting, the MAC address for the router ID, the VLAN that it's on, and then once you've got that, you call the create function, and now what you've done is actually created a router interface in the chip, like in the fast path, to actually mark traffic as routable. So that's step 3. Step 4 is you define your next hop entries. And so if you aren't super familiar with routing, a next hop entry is, it's the next hop, it's the next thing in the L3 path, and that might be the next router down the path. It might be the end point if you're at the end of the path, but really it's how the packet leaves the router. So the internal code will also call this an egress interface, but think of it as the meta information that you need to say, okay, I've got a packet that I'm routing. Which port does it go out on? Which VLAN does it go out on? And what is the source MAC address when I send that packet? Because we've just performed a routing operation. And so, very similar to the interface, there is a data structure called the L3 egress type. It has an initialization function. And then you populate that with the destination VLAN of the new packet, the source MAC address, that is, when the packet leaves the router, what the source MAC address is going to be, the physical port it's supposed to go out, and then the ingress ID that we got from the IP interface on the previous slide. And then you call that, and there's a whole bunch of optional parameters in here. You see the documentation. Like, it's actually the same function that creates tunneling and multicast. There's a bunch of other stuff in here as well. But just in the simple version, we're just doing unicast routing. You take all of that, and you call egress create, and that eventually gets you, as part of the return value here, a next hop ID. So that is a pointer to this resource that you've just created. And then this next hop ID is going to be used in our final step 5 to actually create routes. So just to review, this is how you manage the information for the forwarding memory for how you leave the router. And then once you've got all of this set up, we get to what is ultimately the relatively straightforward part of actually installing routes. Now, internally, these chips actually deal with host routes versus normal routes differently. And so a host route is optimized memory for exact matches. So if you were trying to advertise a /32 in an IPv4 context, that's an exact match. And that you can tell the chip, I'm going to use, if you can give it the hint that it's not a CIDR prefix, it's an exact match, you can get many more, and there's actually different properties for how the chip handles that memory. And the way you do that is depending on which API call you give. And so if you're trying to add a L3 host route that is an exact match route, very similar to other things, you give it a unit, the chip that you're identifying, and an L3 host data structure. And that data structure contains the IP address, the destination that you're forwarding to, and then the next hop ID from the next hop table that you created in step 4. Similarly, if you're adding an actual CIDR route, something with a prefix to it, it's a very similar process, except the data structure is different and contains different information. You have an IP address, a subnet mask, and then the next hop entry. And hopefully those things are actually fairly straightforward. The one that's a little bit less straightforward is you have to actually remember to add a route for your interface from step 3, and then the destination for that route is actually to copy to CPU. What that does is, if somebody is trying to ping your interface, this is actually the thing that creates the map for trying to ping your interface that punt to the slow path, but now the rest of your program can actually handle the ICMP echo reply generation. So all of these things are, I'm trying to call out what are the relevant bits that you need to know. Obviously, there's not a complete implementation here, but there are plenty of implementations, as I mentioned, in the example part of the talk for you to see how this works. So just to recap, 5 easy steps for setting up basic L2, L3 packet forwarding. Set up your slow path, and that's what you use for managing your control plane protocols. Define your port to VLAN mappings. You define L3 interfaces. You define next hop entries, and then with all that together, you can start to install routes. And that gets you a basic L2, L3 router. So just to recap what we talked about what is Open Network Linux. It's a Linux distribution for bare metal switches. What is OpenNSL? It is a an abstraction over the Broadcom SDK that you can get without having to enter an agreement with Broadcom. This lets you write open source code. And then I gave you at least the highlights of what it would take to put together a ONL and OpenNSL programming example. And with that, we're happy to take some discussions. Anything that we said sounded of interest to folks, please consider joining the ONL mailing list. So try to compile the code, try a new platform, try to go with OpenNSL. Kind of a quip for the project is, the feedback is fine, but patches are preferred. And we have growing support for all sorts of OCP switches and non-OCP switches, and there's plenty of videos and tutorials and documentations, including an additional developer-focused talk online. With that, we're happy to take questions. Ellie, did you want to add anything else? Or?
No, I think it's a good coverage of the OpenNSL capabilities with the Open Network Linux. So we are very supportive of this and very happy to collaborate. We see a growing demand for such a platform, and we continue to foster the innovation of that joint platforms. So great review and tutorial, Rob.
Thank you.
Okay, thanks. All right, and with that, I think we have some questions.
Yep, there's one that's come in. There's actually been several back and forth chats, which has been great. So the audience participation engagement is very high. The question is, when will OpenNSL have support for all the field processor qualifier support, which we typically get from an SDK like an L4 header?
This is a good question. So, and I think this is probably a good opportunity to explain how we work with the ecosystem about opening up more APIs. So the kind of the method that we developed is, let's hear our community asking for a specific feature, and we're going to open it up. So the usual development cycle, or the cycle to add new features, it takes about a month. So a customer that builds, we could take an example of either OpenSwitch or FBOSS or any other OpenOS coming to us and say, hey, we need this feature and functionality. We will come and we'll work with the partner, and we're going to enable that. Usually within the same quarter, you will see that API already show up at the GitHub, and of course using our internal process. Specifically for field processors, there were several requests. Most of the requests were around the queue set, the configuration of the field process queue set, the rules, action to block traffic from a specific range of IPv4 source, etc. So those were added, I think, back at...
It's 3202.
Yeah.
I just got that.
Yeah,
I actually just used that code.
So we got dozens of those already open. I mean, we have, I will say, over 50 field APIs that are already open. Similarly, we're waiting and working with our partners to develop the next generation of, or not next generation, but basically the next sets of APIs that we want to open up. And if the request will come, we'll open as we did so far.
Great, great. Any other questions for discussion? I think we're good to go. I don't see others in the queue, and I think we've had pretty great interest in the topic. Thank you, Rob. Thank you, Ellie, for your time today. We really appreciate it. For those online, just head over to our website, bigswitch.com, or you can send us questions in email later at info@bigswitch.com. We work to make it super easy for people to get started. There are 3 easy options to get started with our products. You can get to all of this on our website. The 3 easy ways are Big Switch Labs, and you can experience Big Switch bare metal SDN solutions firsthand from the comfort of your laptop. We think there's no better way to get started with the technology than to just take it for a test drive. Big Switch Labs is free, it's online, it's a real-time access to our products, and you can visit labs.bigswitch.com or download the handout that's in the handout section on the GoToWebinar. The second way is our Community Edition, and this was launched earlier in the year, and essentially gives you free versions of the software products, both Big Cloud Fabric and Big Monitoring Fabric. Both you can find details on the website or in the dashboard. There's a handout available. And finally, our starter kits, which are full, complete solutions that include the switching hardware, our software, support, and cables, and it makes it very, very easy for you to implement your first SDN-style data center pod. And again, if you need more information these options, you can go online or look at the detailed brochures that are available. All of our past webinars, including this one, will be posted online following the event today, and you can get to those by going to one of the green buttons on the home page. Please mark your calendar. Our next webinar is Thursday, September 8th, following VMworld. We'll be at VMworld, so we hope to see some of you there. But we'll be talking about virtual SAN with VMware and Big Switch. Watch your emails for registration details or visit our website. That concludes our presentation for today. Thank you so very much for your time, and we enjoyed talking with you today. Thank you, and have a great rest of your day.